Thank you very much for the introduction of Alex, and hello everyone. I'm Frank. I'm really excited today to talk about our work on the dual-purpose target discovery, as well as the aging research with our precious GPT models. Yes, this is the paper that we published last year in Trends in Pharmacological Science that we talk about how AI can help in the drug discovery, including, for example, the target discovery, indication expansion, and drug repurposing. Okay, and the paper was also chosen by as the editor's choice last year. So, since 2020, we can see that more and more AI-identified targets has been validated with wet lab. And one of the targets has been even moved to the human clinical phase 2. That is our TNIC targets. So it's a very exciting. Okay, and then this is our Insilico approach, how we do the target discovery. So basically, we use multiomics data and text data. We use our 23 AI and bioinformatics models to calculate the score for the interactions of the disease, genes, and the biological process in real time. So that, let's say, we can start from the disease of interest, and then the system will help us to provide a list of the target candidates for the best target for the disease. Or we can start from the target of interest, and then the system will provide a list of the best indication for that particular target. So that is the way how we do the target discovery, indication expansion, and drug repurposing. So early this year, we published a paper that is our lead program, the TNIC for IPF on the Nature Biotech Journal. So as far as I know, it is the most successful and the most comprehensive example to show how AI can really help the drug discovery. So you can see that since 2019, we use our AI platform Pandomics to identify TNIC as the best target for IPF. And since IPF, the fibrosis is kind of an age-associated diseases. So that's why we also do the hallmark of aging assessment. It turns out TNIC has been implicated in several hallmarks of aging. For example, the altered intracellular communications and cellular senescence. So once we confirmed the target, and then we use our generative AI, the Chemistry 42, to design truly novel molecules to tackle this target. And then we went through a series of the in vitro, in vivo preclinical experiments, and then we moved to the clinical within 30 months. So this is another industry record that it moved very fast. And now we already finished the phase 1, and we have moved to phase 2 in both China and US. So since we identified TNIC in 2019 as the best target for IPF, and then we truly believe finding the therapeutic targets implicated in aging is very helpful. So that's why we try to use our Pandomics to very cost-effectively to find the targets integrated in multiple aging disease, because we believe that aging is the driving force for most of the diseases. And then we can also see TNIC is implicated in several hallmarks of aging here. After we identify the targets for multi-age-associated disease, we further classify them into different hallmarks of aging. And then last year, building on this momentum, we focus on whether we can find a dual-purpose target for the treatment of cancer and aging. So that's very interesting. So we collaborate with Evandro from University of Oslo to focus on this study. So basically, we try to identify the targets that is commonly implicated in 11 solid tumors. Those are the common cancer targets. And then we also use the GTAS RNA-seq data to find the targets associated with aging. And then we classify those targets into several groups. So you can see that the green targets are those with evidence in extending lifespan. So here, our definition of the dual-purpose target is that with the same direction of interactions that we can achieve the goal for the treatment of cancer and aging at the same time. So probably you know the best example is the mTOR, the rapamycin example. So however, you can also see that there's over 100 cancer targets that do not have the known effects on lifespan. So next, we are going to propose some dual purpose targets. We propose 23 of them. And the most interesting one is the KTM1A. So from this figure, from panel A, you can see that KTM1A is upregulated in 10 out of 11 solid tumors. At the same time, KTM1A is negatively associated with age. I mean, its expressions. So you can see that KTM1A is downregulated. So I'm not surprised because, you know, mTOR also have the similar situation. So that's why we want to see whether the knockdown of KTM1A can really help to increase the lifespan. So that's, we did the RNA knockdown experiment in the C. elegans, and the result is very impressive. So it is a very good example to show that how AI can facilitate the identification of the dual purpose targets. So yeah, this is the story I want to share today. And now I will pass to my colleague Feder. He will introduce very interesting GPT models. Thank you.